My name's Dylan Beattie, and the first computer I ever had was one of these. This was the Amstrad 6128. It was 1985. I was 7 years old. My dad brought one of these home and he put it in the spare room in our house. This was not a very good computer. And it was all right for 1985. It had a green screen. It came with a couple of very, very dodgy games, like a chess game that I could beat even though I was 7, and a game where you had to throw soap at ghosts who'd invaded a laundrette. But it also came with a thing called Logo. Has anyone used Logo, the programming language? And Logo was brilliant, because I could use Logo to make the computer draw pictures. And it seems weird now, like, we're in 2019. You want to see something on a screen, it's easy. You get your phone out and you type in anything you want, and there'll be pictures and video of that online that you can just download and play and share with people. But back then, just getting something on a screen that wasn't there before was a big deal. You got this, 7 years old, I was digging through these programmers' manuals. The Logo programming manual was not written for 7-year-olds, so I would be sat there working out what all these words mean and trying things out. And when I made the computer do what I wanted and draw this picture, I got this rush, this thrill. It was brilliant. And that's never gone away for me, and I hope for many of you as well. That thrill that you get when you make the machine do what you want, like we failed to do with the AV there for about 10 minutes. Now, over the next 3 days, you're going to see some amazing talks by some brilliant speakers about architecture and unit testing and user interface and experience design. Things that are important and useful and lucrative, if you can sell them to the right people, that help to make software better in terms of as a tool for the world we live in. But I'm not going to talk to you about that. I want to talk to you about something that I think is important, but maybe not as useful as the other things. I want to talk to you about art. Now, there is this famous quote from Oscar Wilde. He said, "All art is quite useless." And maybe it is. Maybe all of you being here is a total waste of your time, and everything I'm going to tell you is pointless, and you should have gone to another talk. Or maybe Oscar Wilde was wrong. I like this quote. "The function of art is to hold a mirror up to nature. Art can help us understand the world that we live in better. And if we want to hold a mirror up to nature, before we can do that, we have to invent the mirror. And that's where science and technology come in. Because for hundreds of years, we've used science and technology and tools to see the world around us in different ways. We had no idea until we invented microscopes that there was this amazing microscopic world hidden right underneath our noses. Things like this, which is the eyelid of a beetle at 200 times magnification. This is crystals growing in a dish of soy sauce. This is the vessels inside the stem of a banana leaf. This amazing beauty we had never, ever seen until we built the tools to allow us to see it. And we've sent telescopes and satellites into outer space. We've looked back at our planet rising over the surface of the moon. We've looked back from beyond the rings of Saturn and seen our pale blue dot down here in the distance. We've even looked into the furthest corners of the galaxy. These are the pillars of creation. They're 7,000 light years away. And we put a telescope in space that took a photograph of them and sent it back to us. And thanks to modern computers, we have been able to start exploring another secret world that's hidden right here under our noses. It's a world of information and mathematics. Throughout the 1970s, a guy called Martin Gardner had a monthly column in Scientific American magazine where he'd share mathematical puzzles and curiosities and games with all of his readers. And of all the columns that he published, the one that had the greatest impact was from October 1970, where he described something called John Conway's Game of Life. Now, the Game of Life, as games go, it is not much of a game. It is a game for one player, played on an infinite board, and it has only 3 rules. The first rule of the Game of Life: each of these little rectangular cells can live it can die, it can be born again. If a cell has 0 or 1 neighbors, it dies of loneliness. If a cell has 2 or 3 neighbors, it survives into the next generation. And if a cell has 4 or more neighbors, it will die of overcrowding. It's a bit like living in London. And finally, the slightly weird, spooky bit, if a cell has exactly 3 neighbors, it will come back to life. And that's it. That is the entire rules of Conway's Game of Life. Now, when Martin Gardner's column was first published, he included this diagram here. He says these are the life histories of the 5 tetrominoes. So these shapes here, you probably recognize those if you've ever played Tetris. And what he's doing is he's plotting out how those shapes evolve over a couple of generations. But looking at it like this on paper is like going to a museum and looking at the butterflies pinned up in the glass case. You can kind of see what they are, but you have no idea what they're like. You don't get any sense of the nature of the evolution of the game of life. So those 5 tetrominoes, let's see what they actually do. Watch this. And so from those 5 shapes and those 3 rules, we get this. 4 of them stabilize, but one of them goes into this infinite looping, repeating pattern that we call traffic lights. And you could understand that using graph paper, but until you start running the stuff on software, you don't really understand. You can't visualize what's really going on here. Even back in the earliest days of doing this stuff on graph paper, people started identifying some configurations which were interesting for all kinds of reasons. One of the earliest configurations they found was found by a guy called Bill Gosper in the early 70s, and it's something called a glider. And the glider is a little shape that just crawls across the grid as it goes. Every 5 or 6 generations, it repeats itself 1 square down and left. And these things keep gliding across this infinite grid of mathematical space. And people started asking questions like, are there configurations in the game of life that will just grow infinitely? Are there configurations that are stable? Can things switch on and off? They started playing around with gliders. Once people started using computers to model this stuff, they found all sorts of amazing configurations, all generated from these same 3 rules, this entire fleet of what we call spaceships. These wonderful, bizarre shapes that just crawl across this mathematical space. In the mid-70s, Gosper and his team discovered something really cool. They were playing around with this idea of gliders, and they created the first thing, what we call a glider gun. Now, the glider gun is a stable configuration, and every 27 generations, it gives birth to another glider and then repeats itself. And it keeps going round and round and round, firing the stream of gliders across the grid. They discovered another pattern, which is a thing called the eater. This thing will consume gliders without destroying itself in the process. Now, on the one hand, this is very cool and very pretty. On the other hand, we've discovered a way to generate signals and a way to destroy signals. We've created truth and false, 1 and 0, yes and no, off and on. And if we have 1 and 0, we have binary logic, right? The question is, can you use the game of life to actually build circuits? So have a look at this. This is an AND gate. Here are 2 inputs, A and B, and this down here is A and B. This is our output. Now, what we're going to do by switching these little eater configurations on and off, we're going to get rid of that one, and now A is true. One of our inputs is true, but our output's still false. We're going to switch on B. Now B is true, but when the pattern stabilizes, our output is still false. If we turn both of those inputs now to be true by removing both of those blockers, and we run our circuit again, we've created a logic gate. We've implemented an AND gate within the game of life. And if we can build logic gates, we can build circuits. And if we can build circuits, we can build computers. And if we can build computers, we can run programs on them, including this program that you might recently have heard about. It's a thing called Conway's Game of Life. And it's a simple cellular automaton based on these 3 very, very simple rules that can lead to the most fascinatingly complex behavior and patterns just from those 3 simple rules. Now, Conway's Game of Life is one of a whole category of systems that start with very, very simple rules and go on to exhibit incredibly complex behavior. You've probably heard of something called the butterfly effect. This idea that long-range weather forecasting is impossible because if a butterfly flaps its wings in Beijing next week, we're going to have hurricanes in Los Angeles instead of sunshine. And all of this is to do with the study of systems that have simple inputs and complex outputs, very sensitive dependencies on initial conditions. The study of these kinds of systems has become known as chaos theory, and it has all sorts of applications. People use chaos theory to study stock market prices, economics, weather forecasting, engineering, but it's also given rise to a whole new field of digital computerized art. Now, to understand what we call fractals and fractal geometry, you've got to get your head around some really weird maths. So here's a piece of graph paper, and we're going to draw a square here, which is 2 by 2. Anyone want to tell me what the area of that square is? 4. Now, we're going to draw another square. This one is minus 2 by minus 2. What's the area of that square? 4. So if 2 times 2 is 4, and minus 2 times minus 2 is 4, how can we get a square whose area is minus 4? Well, we can't. It's completely impossible. And at this point, physics and engineering goes, well, yeah, it's impossible. Let's get on with everything. But mathematicians go, well, hang on. What if it was possible? What if we just make something up? What if we say, all right, we accept that it doesn't exist, so we're going to take the impossible thing, we're going to scribble on our chalkboards here, and we're going to come up with this number I, which we're going to call I for imaginary, because it's not real, and it doesn't exist, and it can't exist, and we've proved it can't exist, so let's play with it anyway, because, hey, mathematics. And this is the rule. We say I is the number that if you multiply it by itself, you get minus 1. And everyone goes, that's impossible, and we go, yeah, it's maths, we don't care. Impossible is we did that before breakfast. Now, when you take these what we call imaginary numbers, and you mix them up a little bit with real numbers, you get what we call complex numbers. Now, a complex number is like a project plan. Some of it is real, some of it is imaginary, and you have no idea what is going to happen next. But we can do arithmetic with these numbers just by following the rules. So we take this number here. This is 0.8 of real stuff, and 1.2 of imaginary stuff. And we can plot this on this graph here. It's a thing called an Argand diagram. And we can actually do equations with these. So we take this number, 0.8 plus 1.2i, and we want to just multiply this number by itself and see what we get. Now, I've color-coded the numbers here. The real parts are red, the imaginary parts are blue. And this is basically high school arithmetic with imaginary stuff in it. We're just going to expand that out, and we can multiply all these terms together. And all you got to remember is anytime 2 blue numbers get multiplied, you take the i's off and the whole thing becomes positive. Negative, negative, square root of negative numbers. And so you expand the thing out, and then you can go through, you can simplify it back down, you add the red bits together, add the blue bits together, and you get an answer out the other end. The arithmetic is not that complicated. Now, for most of history, mathematics has been obsessed with solving problems. If you can't solve a problem, it's not interesting. But during the last century, and particularly the last decade or so, a group of scientists and mathematicians started studying systems where they weren't interested in solving it, they were interested in seeing how it behaved. Let's take a function here. We're going to take some number x, and every time we're just going to do x maps onto x plus 1. So we start at 0, and we go to 1, and 2, and 3. And you can see almost immediately how this is going to behave. This is just going to keep counting up to infinity, right? Let's take another one. X goes to 2 minus x. So we're going to start off here with 2 minus 0 is 2. 2 minus 2 is 0. 2 minus 0 is 2. So within 2 or 3 generations, we're confident we just have this stable, looping, repeating cycle. We understand the behavior of the system, and we can predict what it's going to do 200 generations from now. Let's try the same thing with a complex number. So we're going to take this number here, 0.7 plus 0.8i, and we're just going to square it. And the first time we square it, it goes to there. And we square it again, and it goes to here, and then it goes to here, and then it goes to here, and then it goes flying off into, by the way, there are 4 different flavors of infinity on this graph. So we've got the imaginary positive infinity, the imaginary negative infinity, and then we've got real positive and negative infinities. But that's fine. Don't worry about it. We're not going to go there yet. Let's move that point ever so slightly and run the same procedure over and over again. Now this time it's going to jump to here, and then 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 there. Now the previous one had vanished by this point. It had gone off to infinity. It's never coming back. This one kind of bounces around for a little while. Then it does this. It goes into this sort of weird, almost like a circular pattern for a couple of generations. We cannot predict what it's going to do next. And if we take a bunch of points that are almost next to each other, and we plot in different colors their eventual behavior, we get radically different behavior from starting points that are almost next to one another. In this scenario, the blue line, the pale blue one here, does 1, 2, 3, and then it goes vanishing off to positive infinity. The green one here goes disappearing off the bottom, and then at some point it comes back in on the top and has another go round. The red one is the loop we just looked at. Now, a pair of French mathematicians around 1910 started studying these kinds of shapes, the iteration of complex systems. And they won a medal for it. Gaston Julia and Pierre Fatou were their names. And Julia won a medal for the work they did on that. But they had to do everything by hand. Drawing one of these lines could take them a couple of hours using, graph paper and pencils and stuff. So they never really understood what it was that they had discovered. We didn't discover that until this guy comes along. This guy called Benoit Mandelbrot. He was a Polish mathematician. His family lived in France, then he moved to the US where he did most of his work. He had an awesome job. He worked for IBM, so he had access to computers at a time when most of the world had never seen a computer. And when he got bored, he'd go to Harvard and he'd teach mathematics for a semester, and then he'd go back to IBM with all these new ideas. And he was fascinated by the mathematics of reality. He had this quote which kind of summarizes his philosophy. Clouds are not spheres, mountains are not cones, coastlines are not circles. Bark is not smooth, nor does lightning travel in a straight line. He looked at the jaggedness and the fractured nature of the shapes that are all around us, and he wanted to understand the mathematics that made those kinds of shapes possible. Now, his name has gone down in history because of something that he discovered using Julia and Fatou's work on complex systems and IBM's computers in the late 1970s. And his idea, let's start with this complex grid of numbers, and we're going to take some starting point here, and all we're going to do is we're going to square it and then add the number we started with, and square it and add the number we started with. And we're going to go round and round and round and round with that. Now, his approach here was we're going to run this a bunch of times, say 100 times. And if that number disappears off to infinity and it's not coming back, then we leave it blank. And if after 100 iterations it's still on our grid, then now he didn't really have graphical capabilities, so what he said was, well, we'll just plot an asterisk there on a line printer to give us some idea which of these points in our grid are still going to belong to the set and which ones are going to disappear. And sometime in 1980, he and his team became the first people ever to see this. This is a photograph of the original rendition of the Mandelbrot set. Now, computers got better, they got faster, we invented graphics, we invented colors, and the standard algorithm that some of you here may have played around with is you take the same approach. Z goes to Z squared plus Z, you go round and round and round, and just depending how fast it disappears, you color it in different colors. If it goes vanishing off to infinity really, really quickly, it's blue. If it takes a little while to get there, it's purple. If it's really slow to get there, it's red. And if it never disappears, you color it in black. That's the basic algorithm that we use to draw the Mandelbrot set. Now, the first time I ever did this was on a 286 PC, and I had to start it running, go to school, and when I came back, it had kind of drawn this level of detail. But we have better computers now, which means we can see it in this level of detail. Now, the astonishing thing about this set, that one equation, Z goes to Z squared plus Z, contains a literally infinite level of detail. We're going to start here. This is the Mandelbrot set. How big's that screen? 2-3 meters across, do you reckon? So let's say that now we're at 1 times magnification, and we're going to keep zooming in and in and in and in. When we get to about here, the original set we started with is probably the size of the Radisson Hotel. And there's still all this detail to zoom into. Get a little bigger. By the time we get to about here, the set we started with is the size of Vilnius. And we have more detail. And we keep zooming in, and we get to around about here. The original one is now bigger than Lithuania, and we have more detail. Around about now, it's probably bigger than Europe. Sometime around now, the original one is probably the size of the solar system. It just keeps growing. Now we're stopping here, not because we've run out of detail. There's an infinity of detail at every single one of these tiny little points. And that original graph is now so big that if we start here in a 747 and fly towards the edge, it's going to take us 1,000 billion years to get there. And all of this complexity came out of z is z squared plus z. But there's more to it than that, I think. Because this thing, the Mandelbrot set, somebody has called it the thumbprint of God. Now, I'm not a spiritual man at all, but I do play a lot of computer games. And I like that thing you get in a game where you go off and you do something crazy that you're not sure whether it's part of the quest or not, and you find something there that was put there that says you're on the right track. We left this here for you to find it. And for us to see this, first of all, we had to invent mathematics. Then we had to invent imaginary numbers and work out how to do equations with them. We had to invent computers, which is basically putting lightning inside a rock until it learns how to think. We had to come up with these algorithms. We had to build the rendering systems to do it. And we did all that, and we found this hidden there. And I think that is really cool. Now, computer graphics is not actually that big a deal anymore. 1982, Disney came out with the movie Tron, which Tron was disqualified from the Academy Awards for cheating because they said you couldn't use computers to make films. It wasn't in keeping with the spirit of special effects. It's all right, they gave it a Lifetime Achievement Award later. They sort of saw the error of their ways. But, you know, computer-generated imagery now, Luxo Jr., 1985-86, was the first fully computer-animated film. We had Jurassic Park, which were the first computer-animated characters interacting alongside human actors. A few years ago, this guy appeared on our screens. And if you want to argue, is this the actor Peter Cushing, who's dead, or the fictional character Grand Moff Tarkin, who's not dead, well, Lucasfilm's lawyers would be very, very happy to talk to you. But we have computers now that can recreate just about anything. We can bring anything we can imagine to life. We can say, you know, hey Siri, what would it look like if Friends was remade with Nicolas Cage playing all the parts, and computers just go in and do it? They're like, yeah, we can do that. That's fine. Now, the reason we can do stuff like that is because we have created computers that can learn, computers that can recognize shapes, computers that can see things. Now, you ever lie on your back in a field on a sunny day and you're watching the clouds, and you're like, oh, that's a cat, and that one looks like a rabbit, and that one looks like an airplane, and your brain is seeing all of these shapes that aren't really there. They're just clouds of vapor floating through the sky. And we've started training computers to work in a similar way. We've built something called a convolutional neural network. And what it does, we don't really know how they work, but what we know is if you feed enough photos of, say, cats and dogs through the whole thing, you end up with a network that knows how to recognize cats and dogs. And within certain problem spaces, they actually work pretty well. Now, you might think, well, hey, how hard can it be to tell the difference between a puppy and a muffin? Well, it's often harder than you think, But we've built very, very sophisticated dog detectors into our computers that can look at this and be like, is that a nose or a blueberry? Hang on, let me look at my nose database and stuff. So we've basically built digital dog detectors. Now, the fun happens if you take your dog detector and you reverse the polarity and you say, right, you're a dog amplifier now, and you give it a picture, and the computer says, there's no dogs in this picture, and you go, I don't care, find the dogs. And when you find them, enhance the dogs. And the computer goes, this is a horrible idea, but all right. You're the human here, and you go, enhance. and it comes out with these really weird psychedelic images. Now, this kind of category of art is called deep dreaming. Deep Dream was the first program that 2-3 years ago came out of Google that allowed us to do this. And stuff like this, it's unsettling to look at, isn't it? Because you're looking at it, and what's happening is that some part of your brain is going, dog, 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 and then you look closer like, that's not a dog. I don't know what that is, but I don't like it. What, is dog not a dog? I honestly, because it's exploiting these same kind of pattern recognition things that exist in our brains and in the neural networks. And thanks to that, we've got this entire new category of art that never existed until someone went, what if we turn the dog detector backwards and start inventing dogs where there were no dogs to begin with? Now, I think computers and technology are going to do astonishing things for the whole field of art. It's a demo of a thing come out of Google called Tilt Brush, which is basically augmented reality painting in 3D. And I think computers, technology, augmented reality, virtual reality, some people are going to use it to do brilliant things, some people are going to do it to do not so brilliant things, some people are just going to see what they can make it do for the thrill of going, look, the computer did what I want. Isn't that cool? But I want to move on now. I want to stop talking about using computers to make art, and I want to talk about programming as an art in itself. What if the code was an art form? Now, this is Donald Knuth's famous The Art of Computer Programming. And we have these ongoing debates. What is programming? Is it art? Is it creative? Are there software factories? Are we engineers? You know, what kind of thing is it? And I'm sure some of you have reviewed code that maybe somebody on your team wrote late at night when they were tired, and you've looked at that code and you've gone, this is not art. It's not engineering. I wouldn't call it craft. In fact, I don't know what I'd call it. But the good news is there is a safe outlet, a safe space for that kind of code. And it is obfuscated coding competitions. These are the goals of the International Obfuscated C Code Contest. To write the most obscure program, to show the importance of programming style in an ironic way, to stress compilers with unusual code, to illustrate the subtleties of the C language, and to provide a safe forum for poor C code. Here is a submission from 2015. This is the entire source code for this program. Anyone want to review this code? Tell me what it does? Let's run it, because what the hell? Why read when you can just compile and hope it's not a virus, hey? Oh, there it is. Look at that. It's Flappy Bird in ASCII on a terminal. And even on a terminal, it is still impossibly difficult. Let's have a look at another one. So this is another C source code submission. And this is just a subset of it. If I show you the whole thing, it'll give the game away a little bit. But if you zoom out, so this is a Mandelbrot set generator that runs in a Unix terminal. But it is a Mandelbrot set generator that is shaped like a Mandelbrot set. And this won an award. Now, one of the things about the obfuscated code competition is they try and keep the programs small. What can you accomplish in a really small number of bytes? This is 32 lines of JavaScript. This, if you copy and paste this and open it up in a web browser, it plays chess. And I don't mean it draws a chessboard, I mean it plays chess. It beats me at chess. It is an entire chess engine implemented in that much JavaScript, including the graphics, the board, the rendering, and all the logic of the game algorithm itself. It's called NanoChess, by a guy called Oscar Toledo G, who just keeps winning these programming competitions. He's absolutely brilliant. Now, in 1994, Simon Rasinkiewicz won an honorable mention in the obfuscated C contest for this program. because he submitted it with instructions saying, if you compile it using this specific compiler, it will print its own source code. Because the compiler he was using had a feature where if you gave it the empty input, this is a blank file, if you gave it empty input, it would give you a C program that didn't print anything. Now, he got an honorable mention, and they changed the rules. And they said, your program must be at least 1 character long, otherwise it's just a copy of this one, and that one already won. Which I think is fair, you know. But this gets us onto this whole field of things called quines. Now, a quine is a computer program that prints its own source. Quines, some of you may have come across in this book, Gödel, Escher, and Bach, The Eternal Golden Braid by Douglas Hofstadter. And he's, in this book, discusses a philosopher called William Ormond von Quine, an American philosopher who studied statements that refer to themselves. And so we're going to take this, we're going to spin it into software. How hard can it be to write a program that prints its own source code? And you're not allowed to read the source from disk. That's cheating. You have to actually print it. So we're going to do one now. We're going to build a quine right here in C#. So I'm going to start with this class program, and I'm going to write line program, and I'm going to close my brackets down here, and static void main I'm going to close down here. But now hang on, because I need to console write line the class program, and now hang on. So this, I need to console.write the console. And you very rapidly get tangled up in your own logic. Now, most languages have quirks that you can exploit to get them to print their own source code. In C#, are there any C#.NET developers in the room? Good. Check this out. What we can do is we can put the syntax of our program into a format string, and then we can feed that format string into itself as the thing that should be printed where we've put these placeholders, and we have a C# program that prints its own source code. In JavaScript, this kind of thing is stupidly easy. We just say function f prints f.toString. If you're using ECMAScript 6, this is a valid quine. Now, somebody told me this, and I was like, I do not believe you. So I tried it. And you put that in, and you press go, and sure enough, that function evaluates itself and prints its own source code. And then I found something I think is really brilliant, which is an HTML quine. This guy called Leon Bambrick came up with this idea. It's a web page that prints its own source. So we're going to start with this, HTML head title, blah, 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 /HTML. And when we open this in a browser, it looks like this. Now, we're going to exploit some quirks of the HTML specification here. First of all, we're going to put in a CSS rule that says display everything as a block, even style and head and title, and things that the browser is not supposed to display. And we're going to refresh it. And look at that. Our CSS and our title are now appearing in the page code, and the page rendered output. Now we're going to start exploiting some more CSS rules. We're going to say, well, the HTML element, before one of those, put this content. And after it, put this content. And we refresh again. And there we go. We've got HTML. Now, /HTML is actually here, because it doesn't know where to draw it, but it is there. And if you could scroll down on the screen, you'd see it. Now, to put style around the style sheets, we need to escape the /style, otherwise the parsers have a fight over who gets dibs on that bit, and the HTML parser wins and the CSS breaks, so we escape that. That passes that through. We're going to put some white space formatting on there. We refresh that page again. We go round a couple of times because we need to define rules for each of these different elements, and round and round and round we go. Now, we've got this link here, this A, and that needs to show the href that A actually links to. So we can go in and see, we say, well, before one of these, please extract the attribute value and put that in the content and put that into the page. And there we go, A href equals yada, yada, yada. And I'm just going to put in one more little rule. I'm going to put a 1% height and a margin on the HTML. And there we go, /HTML at the bottom. We have a web page that prints its own source code. Beautiful and completely useless. But how much did you learn about the CSS preprocessor that you didn't know until you tried to do that? Because I learned a hell of a lot doing that. Here is a computer program. What language is this program written in? C++. Well, hang on, let's try it. I'm going to apply some syntax highlighting, okay? So I'm going to apply a syntax highlight here. So we got include standard.io.h, there's main, char star, this is a big string literal, and then a printf. Yeah, all right, C++, probably works on both. I'm going to apply a different syntax highlighter. I'm going to apply a Ruby syntax highlighter, and I'm going to highlight the things that Ruby thinks are string literals. Now, that's interesting, because Ruby thinks this is a valid Ruby program. So which is it? Well, I'll tell you what, let's try running it. So here's our polyquine.c source code. There it is. Now, I'm going to feed that into GCC, and I'm going to run it. We got a warning, but hey, the safety is off well before this point, kids. And look at that. We run it, a.out, and there we go. This is our output from that program. And now I'm going to feed the output of that program into Ruby and see what Ruby... Oh, look, there it is. It's printed itself again. And now, just for the hell of it, I'm going to run the same thing in Python. That's interesting. Because Python's basically Ruby anyway, right? And now I'm going to run it in Perl, because I had to install Perl on my laptop just to make this demo work. And it produces the same thing. Again, this is what's called a polyquine. It's a program that is valid in more than one language and prints its own source code in all of them. And this example runs in C, Ruby, Perl, Python, and C++ if you can find an old enough compiler, because it complains about main not having a return type. But we can do a hell of a lot more. Take a look at this chunk of code here. Now, you're looking at this, trying to figure out what language it's in. It's like, well, we got a system.console here, and so that's probably .NET or C, C#, something like that. But this is an XML, XSL transform namespace, so I don't know what's going on there. This is a for each in a console.log, which kind of smells a bit JavaScripty to me. This is ada.textIO procedure, which I'm guessing is Ada. I'm not familiar with it, but I did look it up. And then, over here we've got begin in block capitals, which means it's probably COBOL, right? Any COBOL programmers in the room? And then up here we've got Act 1, Scene 1, Enter Ajax, which doesn't look like programming at all. This is Yosuke Endo's Ouroboros Quine. It is a computer program written in Ruby that produces a program in Rust, which produces a program in Scala, scheme said, Shakespeare, Slang, Smalltalk, Squirrel, all the way around, and eventually you get an RC program that produces a Rex program that produces the original Ruby program back again. The source code to this program is absolutely stunning. Look at this. That's it. With all this stuff at the bottom where it says buffer for future bug fixes so that they can maintain the exact shape of it. And the most brilliant thing about this, all 128 of those languages, you can apt-get install on Ubuntu Linux. And so there is a continuous integration pipe for this program on GitHub that will run all of those programs. I'm just conscious of time. We started a little late, so we're going to overrun by a few minutes. There's a break straight after this, right? Yeah? Yeah? Cool. All right. Otherwise, I'd have to skip the good bits, and I don't want all of you to miss out. Now, in this Quine, you notice among the COBOL and everything, there was this weird Act 1, Scene 1, Enter Ajax. What's going on there? Well, it turns out there is a programming language called Shakespeare, which is designed for making programs that read like Shakespeare plays. And the way Shakespeare works is that flattering things increment variables and insulting things decrement variables. And so here is the infamous Hello World program. First of all, we have to declare our variables by introducing them. So we have Romeo, a young man with remarkable patience, and Hamlet, the flatterer of Anderson, insulting AS. Act 1, Hamlet's insults and flattery. Scene 1, enter Hamlet and Romeo. Hamlet says, "You lying, stupid, fatherless, big, smelly, half-witted coward. You are as stupid as the difference between a handsome, rich, brave hero and thyself. Speak your mind." That will print H. "You are as brave as the sum of your fat, little, stuffed, misused, dusty old rotten codpiece and a beautiful, fair, warm, peaceful, sunny summer's day. You are as healthy as the difference between the sum of the sweetest, reddest rose and my father and yourself. Speak your mind." E. Speak your mind, L, L. And then this final line here is O. So this little thing here prints the hello in Hello World. Now, I like this because Shakespeare plays were not noted for being short, and neither are Shakespeare programs. And Shakespeare's a lovely example of what we call esoteric languages, esolangs, which are computer programs where the entire programming language is designed to be funny and beautiful and useless. Here is Hello World. Anyone know what language this is written in? This is whitespace, a language that ignores everything except spaces and tabs. Here is syntax highlighting for Hello World in whitespace. Whitespace is a brilliant language for hiding programs inside other programs, because you can put the spaces and tabs in a C program, and the C compiler will ignore them, and whitespace will ignore all the C code. So you can write quines in whitespace really easily. This is the Hello World souffle in the programming language called Chef. Now, Chef is designed for writing programs that are also recipes. And the canonical Hello World involves 72 grams of beans, 101 eggs, 111 cups of oil, 100 grams of mustard, and 33 potatoes. Now, this prints Hello World when you run it in Chef, but it doesn't look like a terribly appetizing recipe. And a few years ago, a guy called Mike Wirth created a recipe, a Hello World in Chef, that is also actually a cake. And he baked it. And, you know, I love this because he came up with this idea of this thing is a valid set of instructions in two completely disconnected domains. If you run it in the Chef interpreter, it prints Hello World. And if you run it in your kitchen, you get a chocolate cake with chocolate sauce that apparently was a little dry, but really quite good. And I love this idea of computer programs that also exist entirely independently as art in their own right. Let's have a look at how to square a number in the programming language called Pete. There it is. That's the program. Pete is a graphical programming language. This is the instruction set. Every time the cursor starts here, and it moves across this grid, and when it travels between two colors, that is an instruction from this set here. Variations in hue and variations in lightness. This is our color palette, light, normal, and dark. And let's look at how that example actually works. So we start there, and when we cross from light blue to dark green, that's a difference of 2 in the brightness, 4 in the hue. Input a number, read some input. Black means change direction. Dark green to dark red, duplicate. Whatever's on the stack, 2 of those. Dark red into yellow, take the 2 numbers off the top of the stack, multiply them, and push that back onto the stack. Yellow into dark red, output whatever's on the stack. So we've squared these numbers, now we print the output. Anything that crosses white is a no-op, no operation. When we get to the edge of the grid here, we change direction. We keep moving inside this blue thing until we end up with black on all sides, and that means halt. The program is finished. This is Hello World in Pete. And it's also just nice. It's artistic. It's the kind of thing you could hang on a wall and nobody would ever know that you were looking at a computer program. And I like that idea. Now, we've talked a lot about this idea of programs that you give to somebody and they run it later and it does something. And we've talked about designing languages and publishing them online. But, we have this idea in software that everything needs to be reproducible, right? We automate everything. Unit tests, integration tests, delivery pipelines, take the humans out of the loop because they might not do the same thing twice. And when you watch live performance, anything can happen. Now, I'm sure there are going to be people here at Build Stuff who are going to do live coding demos. And live coding demos are kind of exciting, right? Because anything can happen. It might work, it might not work. What was it you did, Mark? Exceeded the rate limit on the people issuing the certificates for your demo? Because you rehearsed it so many times, you burned out their quota? And used the last one. Live performance has this excitement and this risk. And in computing, we talk about things that are hard to reproduce as snowflakes, right? We talk about snowflake servers. Don't patch it. Don't run Windows Update. If you even breathe on it, all the finance system will stop working. We've tried putting it in the cloud, and the cloud broke, and now we just locked it in a room and never touch it ever again. But also, if you pick a snowflake out of a blizzard and you watch it melt on your hand, you've just seen something nobody else will ever see. You were part of this unique experience that will never happen again. And that's what makes live performance exciting. This guy here is Sam Aaron. Sam created a programming language called Sonic Pi, which is optimized for doing live performance. And I want to give you a very quick run through of Sonic Pi now. You load Sonic Pi and you do play A4, and it plays a note. Now, Sonic Pi is the only language in the world where everything runs in parallel unless you tell it not to. Imagine if JavaScript ran all your statements at the same time unless you put pauses in. We're going to go in here, we're going to say use BPM, that's beats per minute, and we're going to put a couple of notes in here, and we're going to put in a loop. We're going to say 16 times do this. And we've got a beat. And now we're going to go and we're going to start plugging in a little bit of logic. We're going to put in this variable I, and we're going to say, is I divisible by 3? If it is, play this note. Otherwise, play that note. And then increment I. I is I plus 1. And we've just invented electronic music. Go us, well done. It was much harder when they had to do this with analog. Like, being able to do it on a Raspberry Pi makes everything much easier. But what makes Sonic Pi amazing is something called live loops. So we've defined a live loop here. We've called it my loop, and we've said just keep doing that over and over and over. And now, while that's still running, we're going to drop in down here, and we're going to create another loop, which we're going to call cymbals. And in this loop, we're going to play some sampled drum sounds. Now, first of all, this line here, sync to my loop. It says these loops always start at the same time. Keep them in sync. Keep to the beat. And we're going to say 3 times, play the sample drum cymbal closed. You'll hear what that sounds like in a second. And then we're going to drop in, actually we'll do that 15. Change that around because we've got 16 beats in this bar. We're going to play a drum cymbal open just to close it out. And then without stopping anything, now you hear that? It's dropped in the background. Now, it's doing all of this in real time. It's optimized for live performance. If you've worked on real-time APIs, you can live with 30, 40 milliseconds of latency. That's pretty good, right? Even for like first-person shooters. In music, 40 milliseconds will kill you because everything sounds horrible. It sounds like country music. So we need to keep it absolutely tightly focused. So underneath this Sonic Pi interpreter, there is a thing called Super Collider, which is a real-time audio engine, which is based on Erlang, which means it can patch methods and functions while the program is running and have the old, the current, and the new version in memory simultaneously. So we can do things like write a drum pattern while that melody is still playing. We can come over here, we can drop that loop in, we can fix the name error. There it is. You ready? And now, we're going to come back to our little melody here. And we're going to say, well, if that number I is divisible by 5, I want you to play this note. And if it's divisible by 3, I want you to play this note. And if it's divisible by 15, does anyone recognize the algorithm that's being implemented here? A venerable screening process for recruiting developers? What we've got here is FizzBuzz, implemented in music. And we're going to put a little bit of reverb, and we're going to change some of the effects around a little bit, just to make it sound a little bit more exciting. Not that we get a huge amount through the projector speaker that's up there, but... So that's Sonic Pi. Real-time interactive audio programming. Now, I want to finish up, we have a few minutes left, by telling you about the thing that I did. Because all this stuff about esoteric languages and quines and all that kind of stuff, it gave me an idea. You see, we've always had this trope about this idea of the rock star developer, right? You look at the ads on LinkedIn, and you'll see everyone is out there recruiting for rock stars. Rock star do this, rock star to do that, rock star to do that. And last year, Paul Stovall put this on Twitter. He said, to really confuse recruiters, someone should make a programming language called Rockstar. And I had this experience. I had this moment of blinding revelation. Because, you see, when I wasn't messing around with logo on Amstrads, I was listening to music like this, and I thought, this is what the world needs. The world needs a Turing-complete programming language for writing computer programs that are also 1980s hard rock power ballads. So, the hello world in Rockstar is very easy. It's say hello world, but it's also scream, or whisper, or shout, because creative expression is what Rockstar is all about. Variables and assignment. Now we have int x and we have var mystring and we have the message, and this does not look terribly rock and roll. Now first of all, we don't need semicolons, we don't need types. It's a dynamically typed language. If this is good enough for Ruby, it's good enough for Rockstar. Now we don't want these equal signs. We're going to plug in is instead. Now how many of you ever had an argument longer than 3 hours about whether to use Pascal case or camel case or chainsaw case or snake case or any of these other cases? Because I saw Douglas Crockford give a talk last year when he said we have all these stupid arguments when what we really want are variable names with spaces in them. Now I invented Rockstar in a bar, and when you invent programming languages in a bar, you can do anything you want. So we can have variables with spaces in them. There are simple variables. We have common variables, my heart, your dream, the night, Dr. Feelgood, Black Betty, Billie Jean. Anything starting with capitals, you can chain those together, that's a valid variable name. Now, programming involves a lot of numbers, and rock and roll kind of doesn't. Fizz is 3, buzz is 5, the limit is 100. I wanted a more creative way of initializing variables, so I came up with this. What if we take the lengths of the words, modulo 10, and treat those as digits in a number? So we've got 3, 5, 1, 0, 0. The limit is a love-struck lady killer. That's much more creative than limit equals 100, isn't it? We can do it with floating point numbers as well. You want to initialize pi in C, 3.1415, blah, 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 blah. And JavaScript, var pi equals, well, it's JavaScript, so you're going to get almost pi, like approximately. In Rockstar, my heart was ice, a life unfulfilled, waking everybody up, taking booze and pills. 3.1415. We needed arithmetic. Now in English we talk about, oh, how much is it? It's the price with the tax. It's the total without the tax. The quantity of the product, the distance over the time. Use the same thing in Rockstar, but we can be more creative. We can say a girl with a dream, a man without a face, the wings of the night, a whisper over the water. We need comparison. Your love is a lie, the whiskey ain't the answer. My heart is stronger than steel. My soul is weaker than water. My will is as strong as a lion, and your lies are as low as a snake. You can't program without functions, right? So, modulus takes a number and a divisor. And while a number is as high as a divisor, put a number without a divisor into a number, and give back a number. This blank line, by the way, that terminates the loop, because that's how music works. We don't need semicolons and end statements. If it's a blank line, it means something just finished. Alternatively, midnight takes your heart and your soul. And while your heart is as high as your soul, put your heart without your soul into your heart and give back your heart. So I did this, and I came up with this parody language specification. I stuck it on GitHub, and I tweeted about it. And the internet went kind of crazy. And it made the front page of Hacker News. It got a write-up in Boing Boing magazine. People on Reddit were saying nice things. I don't know if you hang out on Reddit, but getting Reddit to say nice things is no small achievement. It doesn't happen very often. Shut up and take my money. Then this happened. Classic Rock is a real rock magazine that has nothing to do with programming jokes. And they emailed me and said, what's this Rockstar thing we keep hearing about? And they did a feature on it, alongside interviews with the Rolling Stones and Metallica and people like that. I was just like, then people started filing issues. And I was like, why are you filing an issue? And they said, because your specification has undefined behavior. And I said, why do you care? And they said, because my compiler has undefined behavior. And I said, what? And they said, I've implemented a Rockstar compiler in Scala. yesterday. I was like, you can do that? And it just kept going round and round and round. There's about 5 different implementations suddenly sprung up. There's a Scala one and a Rust one and a Python transpiler and all kinds of things. And you know, I like the sound of Dylan Beattie, the creator of Rockstar, but I didn't think that just writing a parody spec in a bar was enough work to justify it. So I decided I actually had to build an interpreter for it if I was going to do this. And I did it over Christmas in JavaScript because I'm an idiot. And for another reason, because I wanted everybody to be able to run Rockstar without installing it. I wanted Rockstar to be a language you can write in a browser on your phone so that everybody can become a certified Rockstar developer. And so I did. Codewithrockstar.com/online. There is an interpreter there. Anybody here can type in some code, run it, and come up and get your official certified Rockstar developer certificates, which are self-adhesive and wipe clean. By the way, the logo here that's on the website, I just want a little tip of the hat to the people I stole that from, because they weren't using it anymore. I wanted something that was really like all out, over the top 80s neon rock and roll, and I looked at lots of band logos. I didn't come up with anything. Then somebody said, have you considered Microsoft Consumer Products, 1980 to 1982, and I went, yes, I'm going to recycle that, so thank you, Microsoft. So that is the story of Rockstar. Now, I'd like your help with something, because I have one little surprise left in store for you today, this morning, and that is the example of the chocolate cake that was also a valid program in Chef. I want to see if we can have a Rockstar program that's also a valid song. And so what I'm going to do is to perform it for you, FizzBuzz, live at Build Stuff, and you can draw your own conclusions as to whether you think this is 2 kinds of art, or 1 kind of art, or no kind of art at all. Is that all right with you? I've just worked out what the problem is. La 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 la. There will be a tiny, tiny interlude while we do that. That's better. Takes your heart and your soul, and while your heart is as high as your soul, put your heart without your soul into your heart. Give back your heart. the top. Midnight taking my world, fire is nothing. Shout this, take it to the top. And midnight taking my world, hate is nothing. Save us, take it to the top. Whisper my word. Thank you, Build Stuff.